Subscribe now.
You are welcome once again in this tutorial. In my previous tutorial, we had some brief introduction on digital signal processing. We talked about a bit, or we mentioned some applications including filtering and also noise reduction and modulation. We also wrote down the mathematical expression for DFT, and then we explained the various representation, which is s of k, x of n, nk, and then the complex exponential kernel 1 or factor. So in this tutorial, we are going to focus on the mathematical analysis of this DFT. So going forward, in DFT, as I've written earlier on, the mathematical expression can be represented by x of k equal to summation of n equal to 0 to n minus 1, x of n multiplying by the exponent j 2 pi over n of k. As I mentioned earlier on, s of k is the frequency domain representation. X of n here it's the time domain representation of the signal. The n represents the total number of samples, and then the k represents the frequency index. So that's this formula. But I can also say that, like in chemistry, there's something called a reversible and irreversible reaction. In the case of DFT, it is a reversible algorithm. That means that when you convert the signal from time domain to a frequency domain, you can also convert that same signal from frequency domain to time domain. So in short, or to make everything simple, I'm going to rewrite this formula and name it the forward DFT and then the reverse or the inverse DFT. Forward DFT. The forward DFT can be written as x of k equal to summation of n equal to 0, n minus 1, x of n exponent negative j 2 pi over n multiplied by nk. And then the reverse or the inverse DFT can also be written as x of n equal to 1 over n exponent n equal to 0, or let's use k rather because it's the inverse. So 1 over n exponent summation of k equal to 0 to n minus 1, and then x of k exponent j 2 pi over n nk. Right, so this is the formula for inverse DFT. So for the forward one, we can say that k is equal to 0, 1, 2, 3, and so on up to n minus 1. It's n minus 1 because if I have a sample, let's say s equal to s equal to 0, 1, 2, 3, over here, the total number of samples inside is 4. But since we are dealing with the fact that the first element represents x of 0, and then it move on x of 1, x of 2, when we are naming it, we will say that the index here is 0, the index here is 1, the index here is 2, and the index here is 3. So the total number of index is what? N, which is 4. And therefore, when we want the last element, it's n minus what? 1. That's how come it is. So for the inverse DFT, you also have n equal to 0, 1, 2, 3, also up to n minus 1. So now let's proceed and then choose some examples, because for the inverse DFT, it has the same representation as that of the forward DFT, just that the arrangement has changed. The exponent, which is the negative aspect, is now positive, and then we have the inverse of the total number of integers, which is the n, multiplying by the x of k as well. So now let's proceed and do some examples. So example 1. If you are being asked that write the mathematical expression for both forward DFT and then inverse DFT, the answer is going to be x of k to be equal to summation n of equal to 0, n minus 1, x of n, exponent negative j, 2 pi over n, nk, where k is equal to 0, 1, 2, 3, and so on up to n minus 1. And then the inverse, this is the forward, and then the inverse 1 is also x of n is equal to 1 over n, exponent k is equal to 0, n minus 1, x of k, exponent j, 2 pi over n, nk, where n is equal to 0, 1, 2, 3, and so on up to n minus 1. So this is the answer to this question. Now, based on this formula that we have analyzed it, let's try and solve another example using this formula, and in this tutorial we will solve different examples whereby we have different numbers of n, where n can be equal to 2, n can also be equal to 4, n can also be equal to 8, and so on. Right. So now let's look at the second example. Find that example 2. Find the DFT for the sequence x of n equal to 5, 8 using direct computation. So this is the question. Now that we understand the formula over here, this is a direct computation of whatever is inside, and we are being asked to find the DFT of it. So solution. So now, what is the DFT for a sample sequence x of n? The DFT of a sample sequence f of n, x of n is x of k to be equal to the summation n is equal to 0, n minus 1, x of n, exponent negative j, 2 pi over n, and then nk. So this is the general formula, right? And then what you need to know is that we have x of n to be equal to 5 and 8. Now we can come out with the fact that n is equal to what? 2, right? Because we have two elements, which is 5 and 8. And looking at the fact that n is equal to 2, we can rewrite the formula as s of k to be equal to the summation of n equal to 0 and then 2 minus 1 of x of n, exponent negative j, 2 pi over 2 nk, right, over 2 nk. So these two will cancel these two, and therefore when you do the simplification, we are going to get x of k to be equal to the summation of n equal to 0 to 1, and then x of what? N, exponent negative j pi n k. So this is simplification. So one thing that you have to know that for the general formula, we have k equal to 0, 1, 2, and n2 up to n minus 1. So based on this, based on the expression that we have gotten here, means that the summation of this expression can go up to n equal to 0 and not 1, right? So now we also have k over there, and k can also be 0 and then 1, because that's how it's supposed to be. So now let's try and then simplify things. For k equal to 0, we are going to get x of 0 to be equal to exponent n equal to 0 and then 1, and we have x of n exponent negative j pi n multiplied by 0. And therefore, when we are doing this, we are going to get the summation for both, right? This part becomes 0 up there, and then exponent power 0 is going to give us 1. So when it gives us 1, we are going to get exponent, the summation of n equal to 0 to 1, x of n, and then multiply by 1. So now that we have 1 here, we can do the summation. If n is equal to 0, we are going to get x of 0 multiplied by 1 plus, when n equal to 1, we are going to get x of 1 multiplied by 1. Right, so this is what the expression that we are going to get. So if we have this expression, what is the sequence that we have? We have the sequence of x of n to be equal to 5 and 8 at x of 0. X of 0 is here, and this one is of x of 1. So now our x of 0 is 5. So we are now going to get 5 multiplied by 1 plus what? 8 multiplied by 1. And for this, when we add them, we are going to get what? 13. So since we have 13 here, we are done with k equal to 0. So now let's do k equal to 1, because we have only 2 elements, which is what? 5 and what? 8, and therefore k can only be 0 and 1. So for k equal to 1, we can rewrite the formula as x of 1 to be equal to exponent n equal to 0, 1, x of n, and then we multiply by the exponent j, and then k is 1, right? So we have pi, and then we have n, and then k is 1 over here. At the end of the day, we are going to get x of 1 equal to the summation of equal to 0, 1, x of n, and then exponent negative j pi n. Negative j pi n. So this is what we have. And when you punch this one in a calculator, you are going to get negative 1, right? Looking at this, we can say that when n is equal to 1 here, the simplification of exponent negative j pi n is going to give us negative 1. So the 1 component is going to give us what? Negative 1. When n is equal to 0, we are going to get x of 1 to be equal to exponent n equal to 0 to 1, right? X of n, and then here will give us what? 0. And because n is equal to what? 0. So when n is equal to 0, we are going to get exponent to be 1, and therefore the 0 part of the formula, x of 0 part of the formula, is going to give us 0, plus when n is equal to 1, the value here is going to give us negative 1. So when the value gives us negative 1, we are going to get the x of 1 here multiplied by negative 1. So looking at the expression, the sequence which was given as 5 and then 8, we have x of 0 to be 5, and then multiply by 1, because this expression is 1, and then here is negative 1, so minus, right? And then x of 1 is 8. So at the end of the day, we are going to get 5 minus 8, and we are going to get negative 3. So now our new sequence is going to be s of k to be equal to 13 and then minus 3. So this is our new sequence. So thank you for watching, and see you in my next video.